Traditional economics often models time as a continuous, unbroken flow, but economic reality doesn't glide. Annual harvests, quarterly GDP reports, yearly tax cycles, these move in sudden, discrete jumps. To measure a system that leaps from one distinct period to the next, we use a specific mathematical tool, the first-order difference equation. When we apply this tool to the real world, it produces wildly different results. It can describe a stabilizing national income, highly volatile agricultural prices, or endless economic expansion. Looking at these paths over time, they appear completely unrelated. You have a smooth convergence to a flat line, a jagged and violent wave, and an exponential curve shooting upward. Despite how distinct these behaviors look on a chart, the underlying mathematical architecture dictating all three models is exactly identical. They are all governed by a single general linear formula, where the value of a variable at time t equals a base constant b multiplied by the variable in the previous period plus another constant, a. The constant a helps establish an equilibrium point, but the system's actual behavior, whether it settles down or spirals out of control, is decided entirely by that base multiplier, b. Look at equation 17.3. To solve a difference equation, we express y without relying on the previous period's value. We need a general solution that defines y for every value of time t, shown here as equation 17.6. That general solution is built from two separate parts, a complementary function, ABT, and a particular solution, which we label C. The C term represents the intertemporal equilibrium, that is, the static level the system would maintain if there were zero deviations. The ABT term represents the time path of those deviations. Within that term, the base multiplier B acts as the engine, dictating whether the system returns to equilibrium or abandons it. Depending on B, there are 7 possible time paths shown here. If B is greater than 1, the path explodes away from the axis. If it's a positive fraction, it converges. If B is negative, it oscillates, alternating above and below equilibrium. A dynamic system does not stabilize just because a theoretical center point exists. Dynamic stability is a strict mathematical property, dependent entirely on the base of that complementary function. Let's test this in a macroeconomic setting. In a basic lagged income model, consumers decide how much to spend today based on the income earned in the previous period. We can format this one-period lag into a difference equation. Look at equation 17.7 here. Notice how current income, YT, is a function of C multiplied by the prior period's income. In this specific economic model, the base multiplier is represented by that lowercase c. That stands for the marginal propensity to consume. By definition, people consume a portion of their new income and save the rest. This means the marginal propensity to consume is a positive fraction between 0 and 1. Because this economic parameter is trapped between 0 and 1, it mathematically maps to a converging time path. The system naturally dampens deviations over time. The psychological limits of human spending habits physically mandate the stability of the system, steering national income toward equilibrium. Agricultural markets operate differently. A farmer plants crops a year before bringing them to market, meaning current supply is strictly dictated by last year's prices.
This delay creates what economists call the cobweb model. When we equate the delayed supply function with current demand, we get a new equation set. Restructuring these terms into our general formula isolates the base multiplier for the price-time path. Here, the base is h divided by b. The variable h represents the slope of the supply curve, which is positive. The variable b represents the slope of the demand curve, which is negative. A positive divided by a negative ensures the resulting base multiplier is strictly less than 0. A negative multiplier mathematically forces the time path to oscillate. If prices are high one year, farmers overplant. The resulting glut crashes the price the next year, causing them to underplant, which spikes the price again. The fate of this market depends entirely on the absolute value of that ratio. If demand is flatter than supply, the path converges. If the reverse is true, the path explodes into total market failure. Boom and bust cycles in agriculture are not random market panics. When production lags behind price signals, Violent overcorrection is an algebraic inevitability. Now we apply difference equations to macro-level growth. The Herod model assumes the acceleration principle. Investment isn't based on total national income, but is strictly proportional to the rate of change in that income over time. Economist Roy Herod sought the warranted rate of growth, the precise path an economy must follow to maintain equilibrium between saving and investment. Setting up Herod's assumptions as a difference equation yields equation 17.14. Look closely at the base multiplier sitting inside the parentheses, A divided by A minus S. The variable A represents the capital output ratio, which is typically a number greater than 1. The variable S is the marginal propensity to save, which is a positive fraction. Subtracting a fraction S from A makes the denominator smaller than the numerator. Therefore, the total value of this base multiplier is mathematically guaranteed to be greater than 1. Applying our stability rules, a base greater than 1 always generates an explosive time path. Unlike the dampening effect of consumer spending or the erratic volatility of crop yields, this system does not seek a flat baseline. The Herod model describes an economy that accelerates constantly, expanding indefinitely without any upper bound, rocketing upward with unrelenting momentum. We started with 3 distinct, seemingly unrelated charts, but mapping the exact economic multipliers, the propensity to consume, the supply-demand ratio, the capital output dynamic, reveals that these different fates are structural variations of the exact same math. Knowing an economic equilibrium point exists is meaningless if the time path is dynamically unstable. The theoretical center point doesn't matter if the forces of the system are mathematically destined to pull away from it. A discrete system survives only if the complementary function, the mathematical calculation of its deviations, approaches 0 as time pushes forward. When examining economic models, look past the static data points. Find the equation, isolate the multiplier, and check the math. In a world built on sudden, discrete jumps, the only reliable way to predict the future is to understand the base of the difference equation.